And 3 responsibilities of the SA node. Increase the signal, set its rhythm to 100 beats per minute, and causes contraction in the atria. And what do we call that? Diastole. Good. Where does the signal go next? AV node. And what's the job of the AV node? Why do we want to delay the signal?
And have the heart contract all at once.
Give the ventricles time to fill with blood. While the atria are contracting, the ventricles are filling with blood. So we delay the signal so ventricles can fill. Then the signal goes down the what? AV bundle and up through the Purkinje fibers, and they cause contraction where?
Ventricle.
The ventricles, which is called what?
Systole.
Systole. Good. So during diastole, atria are contracting and emptying, ventricles are relaxing and filling. During systole, ventricles are contracting and emptying, atria are relaxing and filling. And that's one cardiac cycle. We good on that? Okay. And then we talked about extrinsic control of heart rate, where external things are acting on the SA node to either speed up your heart rate above 100 beats per minute or slow down your heart rate below 100 beats per minute. So what system in charge when you're at rest? Parasympathetic nervous system is in charge when you're at rest. So it's trying to slow down your heart rate, and what nerve does it use? Vagus nerve to act on the SA node to slow down your heart rate. The more active it is, or the higher your vagal tone, the lower your heart rate goes. Okay, so when you're at rest is when it's most active. If you get up and start walking around and then start jogging, your heart rate's going to increase, right? That's from a withdrawal of the parasympathetic system. So the vagus nerve will start to send fewer signals. Your vagal tone will decrease, which will allow your heart rate to increase towards 100. Does that make sense? So it's most active when you're at rest, and it's going to decrease parasympathetic activity as you increase your intensity. Once you get to 100 beats per minute, that's natural sinus rhythm. If you keep increasing your intensity, your heart rate's going to increase above 100 beats per minute. What's in charge of that?
Sympathetic nervous system.
Sympathetic nervous system through what nerve? Sympathetic cardiac nerve, and then epinephrine. And those things act on your heart rate to increase your heart rate above 100 beats per minute. Okay, so if we draw this in a graph, so this is extrinsic control of heart rate. We're going to have intensity on the x-axis. We're just going to say low, medium, high. So that means we're going 2 miles per hour, 3 miles per hour, 4 miles per hour, 5 miles per hour. So we keep getting faster and faster and faster, or whatever the intensity is changing. On the x-axis, we have heart rate in beats per minute. What might be a low heart rate?
60.
Okay. 60 for a fit person might be a resting heart rate. What might be a max heart rate for someone in their 20s?
That would be like 190 something.
100 in the 190s. Okay, so I'm going to put 200 up here. Okay, so heart rate is likely going to range somewhere between 60 and 200 beats per minute. Is it ever going to be 0?
No.
Okay, so I'm not going to start drawing a line down here. It's never going to be 0. Okay, at your lowest intensity, heart rate's going to be its lowest. 60. As you increase your intensity, what happens to your heart rate?
It increases.
It increases, and the relationship is linear. Every time you bump up the intensity, the heart rate bumps up. Every time you bump up the intensity, heart rate bumps up. So it ends up looking like this. If we put 100 beats per minute right here, what's the significance of that?
It's crossover from parasympathetic to sympathetic.
Okay, crossover from parasympathetic to sympathetic, that's true. What do we call this number, 100 beats per minute? The natural sinus rhythm. Okay, so basically, if you're below 100 beats per minute, everything's controlled by the parasympathetic system. If you're above 100 beats per minute, everything is controlled by the sympathetic nervous system. Okay, so if we follow this, we start at low intensity, that's when our parasympathetic system is most active, that's when our vagal tone is highest. As we increase our intensity, 2 miles per hour, 3 miles per hour, 4 miles per hour, heart rate is increasing due to what?
Extrinsic.
Okay, we can't say intensity anymore because we're literally talking about how we control the heart rate. So we can no longer say heart rate is increasing because intensity is increasing. What causes the increase in heart rate from 60 towards 100? It's not the sympathetic cardiac nerve yet. That happens after 100.
Decrease in the vagus?
Decrease in the vagus nerve activity. Decrease in vagal tone. It's a withdrawal of the parasympathetic nervous system activity. Okay? Your sympathetic system is not going to take over until you hit 100 beats per minute. Everything under 100 beats per minute is controlled by the parasympathetic system. So if you are increasing your heart rate from 60 towards 100, it's due to a decrease in parasympathetic nervous activity, specifically a decrease in vagal tone. Do you understand why if you say epinephrine or sympathetic cardiac nerve here, it'd be incorrect? Because we're still in the parasympathetic system. Okay? If we keep increasing our intensity and our heart rate goes above 100, what's causing the increases in heart rate above 100 beats per minute? Increased sympathetic nervous system activity, specifically through increased sympathetic cardiac nerve activity, more signals for the sympathetic cardiac nerve, and the secretion of epinephrine. All of these things act on what part of the heart? The SA node. SA node is control of the rhythm. Okay, so the vagus nerve acts on the SA node below 100 beats per minute. The more active it is, the lower your heart rate. So it withdraws its signals to allow your heart rate to increase towards 100. Okay, above 100, sympathetic cardiac nerve becomes very active. More secretion of epinephrine, those things act on the SA node to increase your heart rate. So if you're up here at 160 beats per minute and you're running on the treadmill and your heart rate's at 160 beats per minute and then you slow it down to a walk, what's going to happen to your heart rate? It's going to decrease back down. Okay? Going back down from 160 towards 100, that's not the vagus nerve. What is it? It's not the vagus nerve. What is it?
The SE.
You get fewer signals to the sympathetic cardiac nerve, less epinephrine secretion. Do you understand how that works? Okay, the higher your heart rate is, the more signals you have going through your sympathetic cardiac nerve, the more epinephrine you have released. Then if you stop exercising or reduce your intensity, that starts to back off. Okay, so everything above 100 beats per minute is modulated by the sympathetic nervous system. Everything below 100 beats per minute is modulated by the parasympathetic nervous system. Yes?
Is the epinephrine secretion controlled by the sympathetic cardiac nerve?
No, it is controlled by the sympathetic nervous system and the endocrine system. Those are two separate things acting on the SA node, but with the same purpose. Any questions about that? Okay, you should be able to draw and label that graph and explain it. And if I give you a scenario of someone doing something like sitting down and then getting up and then walking faster and then jogging and then running and then sprinting, you should be able to explain to me what's happening to their heart rate and why. And it's no longer sufficient to say their heart rate is increasing because their intensity is increasing and they need to pump more blood to their muscles. Okay? That's an answer for a lay person who's never taken a physiology class. That's no longer you. Okay? You have to talk about what's acting on the SA node to control your heart rate. We good?
Yep.
Okay. I think next we get into the terminology. All right? Okay. We talked about cardiac cycle.
Yeah.
Yes.
I'm going to give you some more terminology. already talked about heart rate. And heart rate is kind of one of those things that you know what it is when I use the word, but it's hard to define. How would you define heart rate?
The amount your heart beats per minute.
The number of times your heart beats per minute. Beats per minute. What controls it?
It depends on my activity.
No.
Is it SA node?
SA node. So we call that the effector. The effector is what controls something. It can be acted on to change something. Okay, this is the sinoatrial node. If you want to change the heart rate, speed it up or slow it down, you have to go through the SA node. Okay, so if I ask you about what's affecting heart rate, you need to mention the SA node.
So,
Okay. Stroke volume. Volume referring to an amount of blood. Stroke referring to one contraction of the heart, specifically the left ventricle. Okay, we're mostly concerned with what the left ventricle is doing because that's what's pumping blood to the body. So, stroke volume is the amount of blood pumped by the left ventricle in one contraction.
Is it into the left ventricle or out of the left ventricle?
Out of the left ventricle. Stroke volume, the amount of blood pumped by the left ventricle in one contraction. Okay, the stroke refers to the contraction of the heart.
gotcha.
So, if I have a cup that has 100 milliliters of water in it, I pour some of that water out into a different cup, and then this same original cup, after I've emptied it, now has 40 milliliters of water in it.
How many?
Can you figure out how much water I poured out?
Yes.
How much?
60.
Okay, how did you do that?
100 minus 40.
100 minus 40. Okay, so the amount of water in the cup when it's full minus the amount of water in the cup when it's empty tells you how much water came out.
Gotcha.
Okay, now make this your left ventricle. The amount of blood in the left ventricle when it's full minus the amount of blood in the ventricle after we empty it tells us how much blood came out. Okay, what's the term for how much blood came out?
Stroke.
Stroke volume. The amount of blood that came out in one contraction. So now I'm going to give you the terms for the amount of blood in the ventricle when it's full and the amount of blood in the ventricle when it's empty.
All right.
Okay, it's an amount of blood, so it's going to have the word volume in it. Left ventricle, when it's full, is it going to be full at the end of diastole or at the end of systole?
Diastole.
Systole is when the ventricle is contracting.
Yeah, diastole.
Diastole is when the ventricle is relaxing and filling. So is the ventricle going to be full at the end of diastole or at the end of systole?
Diastole.
Okay. End
Diastolic.
diastolic volume. The amount of blood in the left ventricle at the end of diastole. End diastolic volume is the amount of blood in the left ventricle at the end of diastole. The amount of blood in the left ventricle at the end of diastole. What is the ventricle doing during diastole?
Relaxing.
Relaxing and filling. So that's the amount of blood in the ventricle when it's full. Okay. After we've emptied it, there's an amount of blood. It's a volume. The amount of blood in the left ventricle after we've emptied it. Is the ventricle emptying during systole or diastole? Systole. So end systolic volume. End systolic volume, the amount of blood in the left ventricle at the end of systole. End systolic volume is the amount of blood in the left ventricle at the end of systole. What is the left ventricle doing during systole?
Contracting.
Contracting and emptying. So when it's done contracting and emptying, that's when it's empty. But there's always a little bit of blood left in. We can never get it all out. Okay, so end systolic volume is the amount of blood in the ventricle after we've emptied it. We want that to be a low number. Okay, we want end diastolic volume to be a high number. We want to put as much blood into the ventricle as we can. We want end systolic volume to be a low number. We want to get as much out as we can, leave very little in. The amount that comes out is the stroke volume. Okay, so the formula for stroke volume equals end diastolic volume minus end systolic volume. You need to know what all three of those words mean. Yes.
Is this all only for the left ventricle? Is this what
Left
you're-
ventricle.
That's it,
We're
so
only
the right?
concerned about the left ventricle.
Okay.
Because
Okay,
that's
thank-
what's pumping blood to the body.
Okay, thank you. The other one's to the lung, right? The right
Yes.
ventricle, all right,
The
just
right
making sure.
ventricle goes to the lung.
Thank you.
Okay, the effector for this, or what controls it, is the left ventricular myocardium.
Let's just.
Left ventricular myocardium. Let's use context clues to figure out what myocardium means.
Heart muscle.
Heart muscle
Maya.
of the left ventricle. The more forcefully that heart muscle contracts, the more blood comes out, which will be a higher stroke volume and a lower end systolic volume. Okay, so later we're going to talk about how we get the ventricle to contract more forcefully during exercise. Questions on any of those terms? Yes?
What did you say the end systolic volume was?
The amount of blood in the left ventricle at the end of systole.
Nano what?
The end of
And the
systole,
system.
which is a term we already introduced. Okay, next. Cardiac output. It's abbreviated Q. I have no idea why. The dot on top of the Q means per minute. I won't mark you wrong if you don't put the dot there, but the dot there is going to help you remember the definition. Cardiac output is the amount of blood pumped by the left ventricle per minute.
Okay.
The amount of blood pumped by the left ventricle per minute. Stroke volume is per contraction. Stroke means contraction. Cardiac output is per minute. Okay, and I emphasize the difference between the two. I give you a way to remember it, and I still get people confusing the two. You must understand the difference between stroke volume and cardiac output. Okay, stroke volume is the amount of blood coming out of the left ventricle in one contraction. That's what the word stroke means. Cardiac output is the amount of blood coming out of the left ventricle per minute. What the dot on top of the Q means. Okay, so we can figure out how much blood is coming out of the ventricle per minute if we know how many times per minute the heart is contracting, which is heart rate, and how much blood is coming out of each with each contraction, which is stroke volume. So cardiac output equals heart rate times stroke volume. Elizabeth, do you happen to have your list of terminology or your notes open? Is blood pressure next? ejection fraction and then blood pressure?
Yes.
Okay. Thank you.
Ejection fraction.
Ejection fraction. Ejection fraction is what percent of the blood is pumped out of the left ventricle in one contraction. What percent of the blood is pumped out of the ventricle in one contraction? I shouldn't have erased this drawing yet.
Out of the left or
Left ventricle. So in this drawing from a few minutes ago, we started out with 100 milliliters.
Drop down.
We ended up with 40 milliliters, and we had, that means we had poured out 60 milliliters, right? Okay, so 60 milliliters is the stroke volume. It's an amount of blood. What's the ejection fraction here? 60%. 60% of the blood was pumped out during this contraction. Those numbers are easy because we started with 100. But what if we start with 131 milliliters? And let's still be left with 40. How much should we pour out? How are you figuring that out? 131 minus 40 gives us this, right? End diastolic volume minus end systolic volume gives us stroke volume. So what is it? 191? No, that is
No,
91.
91.
91, thank you. 91 milliliters is stroke volume. What's the ejection fraction?
91 over 130.
91 divided by 131.
69%.
What you have over what was possible to have. What's the answer?
69.
69%. So you need to understand the difference between stroke volume and ejection fraction. One is an amount of blood, one is a percent of blood. How did we figure out the percent? Stroke volume divided by
B to E?
end diastolic volume times 100 to make it a percent.
So,
Okay, so ejection fraction equals stroke volume divided by end diastolic volume times 100. What percent of the available blood was pumped out in one contraction?
and when you do that, we're still rounding off to the two decimal points.
Yeah, I don't typically give math problems for these.
Okay.
It's more conceptual. But if I gave you numbers, you should be able to
Right.
calculate it.
Okay.
And you would go out 2 decimal points.
Just making sure. Thank you so much.
Question? Okay.
Blood pressure.
I feel like I'm missing a term. I feel like I skipped something.
I'm looking at your terminology right now. SBQEF, cardiac cycle, fluids, resistance.
Okay, that's coming here. Okay, thank you. All right, blood pressure. The force exerted by the blood on the walls of the vessels. Blood pressure is the force exerted by the blood on the walls of the vessels. So if the blood is hitting the walls of the vessels forcefully, that's high blood pressure. Okay? Think about the aorta, which is the artery right outside the left ventricle. When the ventricle is contracting, it's emptying, it's pushing the blood very forcefully out, and it's going to hit the walls of the aorta very forcefully. When the ventricle is relaxing, it's filling. There's not blood hitting the aorta very forcefully, which is why there are 2 numbers in blood pressure. What are they called?
Systolic, diastolic.
Systolic and diastolic. Systolic blood pressure is blood pressure during systole. What is the ventricle doing during systole? Contracting. Diastolic blood pressure is blood pressure during diastole. What is the ventricle doing during diastole? Okay, so what's a normal blood pressure?
120 over 80.
Yeah.
Anybody know the unit for that? You guys do blood pressure in your lab?
Millimeters per hour.
It is millimeters of mercury. 120 over 80. Which number is systolic blood pressure?
Top.
The top number. Bottom number is diastolic. Systolic is always much higher than diastolic, which makes sense because during systole, ventricle is contracting, blood is hitting the wall of the aorta very forcefully, blood pressure is high. During diastole, ventricle is relaxed, blood pressure is low. When you increase your exercise intensity, what happens to systolic blood pressure? It goes up because the ventricle is going to contract more forcefully. Blood is going to come out harder. During diastole shouldn't go up. Ventricle is relaxed. If diastolic blood pressure increases during exercise, that's an emergency and you need to see a doctor immediately. It shouldn't happen. But it's normal for systolic blood pressure to go up. Yes.
What do you say the 120 stood for?
That is blood
Systolic.
pressure during systole. Systolic over diastolic blood pressure.
So the 80 would basically never change unless you had like a medical emergency, pretty much. No, that should always stay constant, no matter
It
what.
should, yeah. It
Right.
might even drop a little bit.
But not much. Like, it should never drop like,
It shouldn't drop a lot.
yeah, okay, cool.
I'm gonna give you a formula for this in a second. First, I have to give you peripheral resistance. Resistance is what the heart has to work against to try to move the blood out. Resistance is what the heart has to work against to push the blood out. If resistance is high, there's a lot of resistance to pumping the blood out. It makes it harder to pump the blood out. If resistance is low, it's easier to pump the blood out. Okay, so it's what the heart has to work against to move the blood. Peripheral resistance depends on the length of the vessel times the viscosity of the blood divided by the radius of the vessel to the fourth power. Peripheral resistance equals the length of the vessel times the viscosity of the blood divided by the radius of the vessel to the fourth power. And before I go into the details of that, I'm going to give you the formula for blood pressure. Because blood pressure equals cardiac output times peripheral resistance. What's cardiac output?
Heart rate times stroke volume.
Okay, so we can spread this out through the expanded formula. Blood pressure equals heart rate times stroke volume times length times viscosity over radius to the fourth. Okay, this is peripheral resistance. This is cardiac output. Are you with me?
Yes.
Okay. Let's talk about peripheral resistance. The length of the vessel. Let's imagine you and your friend are both drinking water out of a straw. You have a regular 6-inch straw, and your friend has a 6-foot-long straw. Who's going to have a harder time drinking the water?
6 foot.
Can you imagine trying to get water through a 6-foot-long straw? There's a lot of resistance. Very hard to get the water to flow through. Okay, so if we think of that as the length of the vessel, the longer the vessel, the more resistance there is to the flow of blood. It's harder to move the blood through a long vessel. Okay, so an increase in the length of the vessel will cause an increase in resistance. Makes it harder to move the blood. That increase in resistance is going to cause an increase in blood pressure because it's going to force the heart to pump more forcefully.
Does this mean that tall people have higher blood pressure?
But you also probably have a bigger heart.
Ah, okay.
Can we change the length of our vessels?
No.
We actually can.
What?
Because if you gain weight, if you add tissue, whether it's muscle or fat, you have to vascularize it. You have to deliver oxygen to it. So, gaining 1 pound of fat adds something like 400 miles of vessels.
What?
Adding 1 pound of fat adds about 400 miles of vessels. So, the longer your vessels, the harder your heart has to work, right? Higher your blood pressure. So imagine the heart of someone who is obese. How long their vessels are and how hard the heart has to work, how high the blood pressure is. That's why obesity and blood pressure are linked. Go ahead.
Is it because of what the increase in surface area the person has now? Or that's the
Well, this is specifically the length of the vessel. So there is an increase in surface area, but that's not related to blood pressure. That has more to do with metabolic rate.
So is this not the same for like when you gain muscle then?
Muscle as well.
Oh, so muscle and, but
Muscle.
is that ratio pretty much the same?
I'm not sure what the number is for
Oh,
muscle.
okay.
The good news is, if you lose the weight, the vessels will shorten. But definitely a link between obesity and blood pressure, and a link between blood pressure and heart disease. Okay, viscosity of the blood. Viscosity basically means thickness. If something is viscous, it's thick. If viscosity is high, that means it's thick. Okay? If viscosity is low, it would be thin. So, you and your friend now both have regular 6-inch straws, but you're drinking water and your friend is trying to drink chocolate pudding through the straw. Who's gonna have a harder time?
Chocolate
Okay,
pudding.
chocolate pudding is thick, it's viscous. There's a lot of resistance to the flow through the straw. Okay, so the thicker your blood is, the higher the viscosity, the more resistance there is to the flow. So an increase in viscosity would cause an increase in resistance, would cause an increase in blood pressure. Can we change the viscosity of our blood?
Yes.
Yes.
We can. How?
Hydration.
Primarily through hydration. So if you are dehydrated, if you're doing something that makes you sweat a lot, most of that sweat is plasma coming from your blood, which is going to make your blood thicker. If your blood is thick, it increases resistance and increases blood pressure, which is one reason it's very important to stay hydrated, especially for someone with heart disease. Because someone who's obese, for example, has very long vessels, already has high blood pressure. Then if they go and do some kind of strenuous physical activity and don't hydrate, now their blood is also thick, and it raises the risk of having a heart attack because it spikes your blood pressure. So you can avoid that by staying well hydrated. Radius is how wide or narrow the vessel is. Okay, if the vessel gets wider, that's an increase in radius. If the vessel gets narrower, that's a decrease in radius. So you and your friend are both drinking water out of a straw. You have one of those big fat smoothie straws, and your friend is using one of those tiny little red straws that you're supposed to use to stir coffee. You ever tried to drink water out of those?
Yep.
Or coffee out of those? It's difficult, right? The narrower the vessel is, the more resistance there is to the flow. It's hard to get a liquid to flow through a narrow vessel. Okay? Which means a decrease in radius. The vessel getting narrower will cause an increase in resistance, will cause an increase in blood pressure. Notice the relationship is different. right? Length and viscosity have a direct relationship to peripheral resistance and blood pressure. One goes up, the other goes up. Radius has an inverse relationship. It goes down, resistance goes up. That's why it's underneath. That's what that means. Can we change the radius of our vessels? We can. How? What's it called when our vessels get wider and narrower?
Vasodilation.
Vasodilation.
Vasoconstriction.
Vasodilation is an increase in radius. Dilation means it's getting bigger. Vasoconstriction is a decrease in radius. Vessel getting narrower. We mentioned briefly on Monday where this occurs. Remember this? We have vessels that bring blood towards the muscle and vessels that bring blood towards the heart. What were they called? Arteries, arterioles, capillaries, venules, veins. Which are the vessels that have the smooth muscles that can contract and relax? The arterioles. This is how we control blood flow. If we want less blood flow going to this area because it's inactive, what do we do to this vessel?
Constrict.
Vasoconstrict. That's a contraction of the smooth muscles of the arterioles. Causes vasoconstriction, decreases blood flow to that area. If we want more blood flow to this area because it's active, what do we do to this vessel? Vasodilate. That's a relaxation of the smooth muscles in the arterioles, making it wider, increasing blood flow to the area. So this is how we control blood flow, by vasoconstriction and vasodilation. So we can redirect blood flow to the areas where it's necessary. Okay, if you've just eaten, you need blood flow going to your digestive tract to help you digest. If you're riding a bike, you need blood flow to your quads to help you exercise there. If you're doing something overhead, you need blood flow to your upper body to do exercise there. Okay, which is why a full body exercise feels more difficult than an isolated exercise, because there's competition for blood flow, right? If you're only pedaling on a bike and you mainly just need your quads, we're gonna vasoconstrict everywhere else and vasodilate to your quads. Blood flow goes there. If you're just doing upper body, we can vasoconstrict to the lower body and send the blood where we want it. If you're doing something that involves multiple muscles across the body, you need blood flow everywhere, so there's competition, so there's less blood flow to each individual area, so that's gonna feel harder. Questions on that? This is also why you are not supposed to swim right after you eat. Were you guys all told that as kids? They still said you have to wait 30 minutes after you eat before you swim. Because if you just ate, blood's going to your digestive tract. If you swim, you need blood going to your muscles. And so you end up with a cramp. Cramp is ischemia, lack of oxygen to your diaphragm because there's competition for blood flow. In a pool, that can be dangerous. Okay? Really, you shouldn't be exercising any type of exercise 30 minutes after you eat because of the competition for blood flow. But swimming is singled out because it's dangerous. But it's gonna happen if you try to go for a run right after you eat, same thing's gonna happen. Competition for blood flow. Okay. To give you more terminology here. Anything you want to ask me before I go on? We're going to talk more about controlled blood flow. Yes?
Why do you say that the blood flow is dangerous again?
The competition for blood flow is dangerous if you're in a pool. Because if you're getting cramps and you're not getting enough oxygen, you don't have enough blood flowing to your muscles to keep you afloat, then you could drown. If you were running, you would just stop running. But you can't just stop swimming.
When you have a collection of cholesterol, is it collecting there the smooth muscle?
It could be in
Any part?
any vessel. It's typically, when it's causing heart disease, it's typically in the coronary artery that feeds the heart.
Okay.
So it's blocking blood flow to the heart muscle itself.
Itself, okay. Thank you.
Okay, so arterioles control blood flow through vasoconstriction and vasodilation. So we're gonna talk about how we cause vasoconstriction and vasodilation, okay? There is intrinsic control of blood flow and extrinsic control of blood flow. What does intrinsic control of blood flow mean? Arterioles controlling themselves. What does extrinsic control of blood flow mean? Something else is acting on the arterioles. Okay, we're gonna start with extrinsic control. What time is it?
12. Game time.
Extrinsic control of blood flow, not to be confused with extrinsic control of heart rate. If we're talking about extrinsic control of heart rate, we're talking about external factors acting on the SA node. If we're talking about extrinsic control of blood flow, we're talking about extrinsic factors, external factors acting on arterioles. Common to confuse those two. Okay. Epinephrine acts on arterioles to cause vasoconstriction. Epinephrine causes vasoconstriction. When is epinephrine secreted? During exercise. So if you're exercising, you're secreting epinephrine. Epinephrine's now in your blood. It's going around in your body, and the arterioles have receptors for the epinephrine. When they get the epinephrine, it's going to cause the smooth muscles to contract, and you're going to get vasoconstriction. There are two exceptions to that. One is at the vessels near your skin. The vessels near your skin have different receptors, and so they respond to epinephrine differently. The vessels near the skin will respond to epinephrine by vasodilating. What happens to your blood flow if we vasoconstrict everywhere except near your skin? Where's the blood gonna go?
To your skin.
Why do we want that to happen?
Sweat.
Thermoregulation. We bring your blood closer to the skin to dissipate heat and to sweat. Because the sweat is plasma coming out of your blood. Goes through your skin and evaporates into the air, and that cools off your skin. Okay? So epinephrine is causing vasoconstriction everywhere except at the vessels near the skin where it's causing vasodilation. And that helps us thermoregulate, helps us sweat. Sweating is a good thing because it's thermoregulation. You're not trying to stop yourself from sweating. You need sweating for thermoregulation. So I said there were two exceptions. Where else do we need to increase blood flow when we're exercising besides to the skin?
Heart.
To the exercising muscle. Right? If I'm pedaling against resistance on the bike, I need blood flow to my quads. Epinephrine is causing vasoconstriction everywhere except at the vessels near the skin where it's causing vasodilation so we can sweat. And then we need another mechanism at the exercising muscle so we can vasodilate at the exercising muscle. And then we're gonna be redirecting the blood to the skin and to the exercising muscle. Okay? The way we get vessels to vasodilate at the exercising muscle is through intrinsic control of the arterioles. Okay? Extrinsic control is epinephrine causing vasoconstriction everywhere except at the skin. Intrinsic control blood flow is their arterioles controlling themselves. This specifically happens at the exercising muscle. Okay, so if this muscle is active, what's it likely to produce? Lactic acid. So lactic acid levels are high. My pens are dead. What else is it likely to produce? Hydrogen goes along with that.
Carbon.
If you've got a lot of hydrogen and lactic acid, what happens to your blood pH?
Goes down. Increase the density.
If this muscle is active, it's consuming a lot of oxygen. So oxygen levels are low. It's producing carbon dioxide, so carbon dioxide levels are high. And what's happening to the temperature at the exercising muscle? Okay, these are conditions that you'd expect to see at an exercising muscle. You should understand why all of these are happening. These are conditions you'd expect to see at an exercising muscle. What sensory receptor is going to sense most of these? The thermoreceptor will sense the temperature. What's sensing the rest of them? Chemoreceptors. Chemoreceptors sense, I'm going to call them the local conditions at the exercising muscle. You need to be able to list them. And they will cause vasodilation to the arterioles in that area. So, we're sitting on a bike, pedaling against resistance. That's mainly our quads. The conditions in our quads are going to look like this. Lactic acid, hydrogen, low blood pH, low oxygen levels, a lot of carbon dioxide being produced. Chemoreceptors are going to sense that and cause vasodilation in these arterioles. That brings more blood flow to this area, which is exactly what we want. That blood flow is going to bring oxygen. It's going to clear out carbon dioxide. It's going to clear out hydrogen. It's going to clear out lactic acid. It's going to normalize the temperature. That's a negative feedback loop. Right? Local conditions sensed by the sensory receptor causing a response cancels out the stimulus. Negative feedback loop. Question?
So does chemoreceptors play off the baroreceptors, or is it vice versa, or do they have like a coexistence?
Baroreceptors are different sensory
Right,
receptors. Those are
from
for blood pressure.
All right, that's how.
Chemoreceptors are for chemical changes in the blood.
Okay.
Okay, so let's recap control of blood flow. Extrinsic control of blood flow is something external acting on the arterioles. That's epinephrine. When you're exercising, you secrete epinephrine. The more intense your exercise, the more epinephrine you secrete. Epinephrine acts on the SA node to cause what? Increase the heart rate. Epinephrine also acts on the inspiratory centers of your brain to cause an increase in breathing rate. Epinephrine also acts on the arterioles to cause vasoconstriction everywhere except at the vessels near the skin where it causes vasodilation, helping you thermoregulate, making you sweat. And then at the exercising muscle, in this example, in your quads, you're creating these conditions that are sensed by the chemoreceptors that cause vasodilation. So it's happening when you're pedaling against resistance on a bike. You've got vasoconstriction everywhere except at the skin and at the exercising muscle. This is exactly what we want to happen. This is helping us exercise. Okay, you need to understand the mechanisms behind this. Questions? Okay, so all of that goes here. How we control the radius of the vessel through vasodilation and vasoconstriction. So we've got vasodilation and vasoconstriction happening at the same time in different areas of your body, right? Vasoconstriction from epinephrine everywhere except at the skin, where epinephrine is causing vasodilation, and at the exercising muscle, where the chemoreceptors are causing vasodilation. Okay? One more term I need to give you here. Sympatholysis. So, let me give you the definition first and then we'll talk about it. Sympatholysis is the ability to vasodilate at the exercising muscle. Sympatholysis is the ability to vasodilate at the exercising muscle even in the presence of epinephrine, which is trying to cause vasoconstriction. Sympatholysis, the ability to vasodilate at the exercising muscle even in the presence of epinephrine, which is trying to cause vasoconstriction. We'll say it one more time. Sympatholysis is the ability to vasodilate at the exercising muscle, even in the presence of epinephrine, which is trying to cause vasoconstriction. Okay, now you can memorize that as a sentence and have no idea what it means. But if you can process what it means, it's going to be a lot easier to memorize or understand or remember. When you're exercising, you're secreting epinephrine. Epinephrine is causing vasoconstriction. If you were trying to push pedals on a bike and the arterioles in your quads were vasoconstricting, you wouldn't be able to push much resistance because these conditions would build up. Blood pH would drop, and you should be able to explain to me in detail how that's causing fatigue. Your legs are going to be burning and you're not going to be able to keep pushing, like hardly at all. In order for you to continue exercising with those muscles, we need to bring in blood flow, to bring in oxygen and clear out those conditions. So we have to be able to overpower the epinephrine in the exercising muscle. That's what sympatholysis is. The ability to vasodilate at the exercising muscle, even though epinephrine is there, trying to cause vasoconstriction. Okay, so there's this battle between epinephrine trying to cause vasoconstriction, chemoreceptors trying to cause vasodilation. There's a battle. Who wins the battle? Who wins the battle?
It depends.
No, it doesn't. What happens if epinephrine wins the battle? You can't exercise.
Yeah.
Who wins the battle? Chemoreceptors have to win that battle so that you can exercise, so that you can get increased blood flow to the exercising muscle. That's sympatholysis. Okay? So if I ask you to explain sympatholysis, this is what I typically get. Sympatholysis, local conditions at the muscle sensed by the chemoreceptors causing vasodilation. Is that sympatholysis? No, that's intrinsic control of blood flow. The fact that intrinsic control of blood flow overpowers the extrinsic control of blood flow is sympatholysis. It's different. The process of doing that is intrinsic control. This process overpowering the epinephrine is sympatholysis. Questions? Yes?
Is there like a time when like the epinephrine wins over the chemoreceptors, or is that just not ever gonna happen?
So the more intense these conditions are, the more blood flow you're gonna get. So it's not like either on or off, it's more of a continuum. So if you're doing light work, you're not gonna have a whole lot of, like if you're working aerobically, you're not gonna have a whole lot of these conditions, and so there's gonna be less vasodilation. You have to be doing more intense work to get the vasodilation because creating these conditions. Yes?
So does that explain the pump that people feel during like intense exercise?
The bump,
Pump.
the pump,
Yeah.
the pump is actually plasma going into the muscle. Like when you're talking about when you're lifting weights, that's actually plasma going into the muscle. It's actually swelling. But that is a real thing.
It's temporary.
It is temporary.
Yeah.
Yeah, we talk about that in the resistance training chapter. Okay, next I think we talk about blood pressure, yes?
Those have
Okay.
hypertrophy.
I'm going to erase, I should leave that one up there.
Take a picture real quick.
Yeah, I'll leave it up there. I'm gonna erase these words. Is that okay? Cardiovascular drill. That would be a-
Just in case.
Okay. What is the short formula for blood pressure? Cardiac output times. Okay.
Yeah.
I strongly recommend that you say the words instead of the letters.
Peripheral resistance.
When I'm writing this, in my mind, it sounds like blood pressure equals cardiac output times peripheral resistance, not BP equals Q times PR. Okay, say the words in your head so that you know what these mean. Okay, if we expand that, how do we expand cardiac output?
Heart rate times stroke volume times length versus viscosity.
Viscosity
Over
radius to the fourth. Peripheral resistance, cardiac output. Okay, I'm writing this big because I'm going to add detail here.
You need another marker?
Okay, what happens, so we're talking about now acute control of blood pressure, or what causes your systolic blood pressure to increase during exercise. Okay, we said it's normal for systolic blood pressure to increase during exercise. This is what causes that. If we're talking about what causes something, we've got to look at its formula. Okay, your blood pressure depends on your heart rate, your stroke volume, your length, your viscosity, and your radius. So, what happens to your heart rate when you're exercising? It increases. Why?
We just went over that because of SA node.
Something's acting on the SA node,
Yeah.
right? So the SA node is my effector here. We talked about 3 things that act on the SA node. What are they?
Epinephrine. The SCN.
Say the words.
Sympathetic cardiac.
There you go.
I'm gonna abbreviate it, but you need to know what it stands for and how to spell it. Okay, so what I'm doing now is I'm making a flow chart. Starting with increased exercise intensity, explaining the increases in blood pressure. Okay, so how do we link the increase in exercise intensity to the vagus nerve?
Has to decrease.
What is it?
The vagus nerve decreases, right? As
It does.
exercise.
What should I put in here? Sympathetic nervous system or parasympathetic nervous system?
Parasympathetic.
Okay. Is the parasympathetic nervous system activity increasing or decreasing?
Decreasing.
Increased exercise intensity causes a decrease in parasympathetic nervous system activity, causing decreased activity of the vagus nerve. I'm going to say decreased vagus nerve activity. You can say decreased vagal tone. Same thing. Acts on the SA node to cause what?
And
Increase in heart rate. That increase in heart rate increases cardiac output, increases blood pressure. Okay, so this is a flow chart explaining in detail what causes systolic blood pressure to increase during exercise. So you increase your exercise intensity, that decreases parasympathetic activity, decreasing the activity of the vagus nerve, allowing the SA node to increase its rhythm towards 100 beats per minute. That increases cardiac output, which increases stroke volume. We okay on that one? Yes.
Can you give me to where like Vegas and activities drops? Like from after that does cost. Yeah.
After this,
Yes.
so the vagus nerve, when it's sending a lot of signals, acts on the SA node to slow down the heart rate. So if it's giving fewer signals,
SA node.
it allows the SA node to speed up. The less active the vagus nerve, the higher your heart rate, because it's parasympathetic. Okay, connect me from increased exercise intensity to the sympathetic cardiac nerve.
Let's go to the sympathetic nervous system.
Increased sympathetic nervous system activity causes increased sympathetic nervous system activity,
Epinephrine.
which acts on the SA node to increase heart rate, increasing cardiac output, increasing stroke volume. Sorry, blood pressure.
Same thing with epinephrine.
Okay, same thing. Increased epinephrine secretion acts on the SA node, heart rate, cardiac output, blood pressure.
So the stroke.
Okay, so question I could ask for this: explain in detail how the heart rate is involved in increasing blood pressure during exercise. Starting from increasing exercise, we have three things, three pathways acting on the SA node to increase heart rate. And then you connect heart rate to cardiac output to blood
To
pressure.
blood pressure.
Stroke volume, what's the definition of stroke volume?
Any diastolic volume minus
Okay, that's the formula, what's the definition in words?
The
Amount of
amount of
blood.
It's the amount of blood
that's out of the left ventricle.
Per contraction, what's the effector?
SA node.
The myocardium.
Oh.
Remember, the more forcefully the myocardium contracts,
Oh, that's right.
more blood comes out. So the effector here is the left ventricular myocardium. I'm abbreviating it.
Left ventricle.
Make sure you know
Left
what
ventricle.
it stands for. So, I said during exercise, something is going to act on the left ventricular myocardium to convince it to contract more forcefully. What do you think that is? What is going to act on the left ventricular myocardium to tell it to contract more forcefully?
AV node.
Purkinje fibers.
I will give you a hint. Anytime you need to guess what is controlling something during exercise, your best guess is epinephrine. Because epinephrine controls almost everything during exercise. Okay, so epinephrine is acting on the left ventricular myocardium to increase its contraction strength. If we increase the contraction strength of the left ventricular myocardium, what does that do to stroke volume? More blood's gonna come out. That increase in stroke volume will increase cardiac output, will increase blood pressure.
Right above LBM, I'm sorry.
Increased contraction strength. So the epinephrine acts on the left ventricular myocardium, making it contract more forcefully. That makes more blood come out.
Okay.
Anything happening to the length of your vessel during exercise?
Turn? No.
Not during exercise.
No.
Anything happening to the viscosity of your blood during exercise?
Yes.
What?
You might get dehydrated.
Yeah, it decreases.
So what happens to the viscosity if you get dehydrated?
It increases.
Okay, so let's walk through that process of becoming dehydrated during exercise. Start from an increase in exercise intensity and get me to an increase in viscosity.
Okay, I was about to say, what's the increase?
This is the critical thinking part, because you have this information.
Can you repeat that question?
Yes, get me from an increase in exercise intensity to an increase in viscosity. This causes this, causes this, causes this.
Exercise.
What is it?
Increases, there's an increase in epinephrine, which increases sweating.
How? Vasodilation where? So epinephrine causes vasodilation at the vessels near the skin.
Epidermis,
Causing
Sweat,
sweat.
thermal regulation, I guess,
So that sweat is coming from the plasma from your blood. So if we lose water from the blood, that makes the blood thicker. I'm actually gonna add a term here that I haven't talked about to you yet, but we'll need it there for later. So this is gonna increase hematocrit, which basically means the same thing as increasing viscosity. I'll give you that term next week.
Hematocrit.
Increasing viscosity. So you're losing water from your blood, so your blood is thicker. That increase in viscosity causes an increase in resistance, causes an increase in blood pressure. I'll explain the hematocrit next week. Anything happening to the radius of the vessels during exercise?
Yes.
Yes, what?
Vasodilation.
Yeah.
Vasodilation and vasoconstriction.
Yeah, but,
They're
yeah.
both happening. Are they both gonna contribute to what we're talking about?
Yes.
Are they?
Well, if you have vasoconstriction, we need an increase in blood pressure.
In order, we're trying to explain an increase in blood pressure,
So you would have
which means we're trying to explain an increase in resistance. So what has to happen to the radius to cause an increase in
Has
resistance?
to constrict.
Yeah.
If we talk about an increase in radius here, which is happening, it doesn't contribute to what we're talking about. So it doesn't belong on here. Okay, we're explaining the increases in blood pressure. So yes, the vasodilation is happening, but it doesn't contribute to what we're talking about. So we're talking about vasoconstriction causing the decrease in radius. Get me from increased exercise intensity to vasoconstriction.
You would have epinephrine would still play another part.
Acting on
The
Arterioles.
Yeah, arterioles, thank you.
causing vasoconstriction, which is a decrease in the radius. Causing an increase in resistance, causing an increase in blood pressure. Okay, so this is a concept map or a flow chart detailing for you acute control of blood pressure. What causes increases in blood pressure during exercise? You increase your exercise intensity and it causes all of this to happen. Notice the role of epinephrine. How many pathways here do we have with epinephrine?
It plays part in all three.
Epinephrine
4. Yeah.
is acting on the SA node to increase heart rate. Epinephrine is acting on the left ventricular myocardium to increase stroke volume. Epinephrine is acting on the arterioles to cause vasoconstriction to increase resistance, and it's causing you to sweat, which decreases viscosity. Epinephrine has a huge role here. Okay? I am not going to ask you to draw this map, but I'm going to ask you questions about the acute control of blood pressure. For example, explain in detail 4 ways that epinephrine is involved in the acute control of blood pressure. Being able to draw this map is going to help you organize your answer. Okay, so I'm not going to ask you to draw this map, but I am going to ask you questions about blood pressure. Okay, I'm done. That's a lot of information.
Bang, bang.
You have